Hello, in this recording I'm going to talk about discrete probability distributions. So this is the continuation of the topic of random variables that we talked about in a previous recording. So we looked at random variables, discrete versus continuous. We focused on the discrete. And we looked at the probability distribution functions in that case. And we saw also, or we talked about cumulative distribution functions, and we looked at some of the properties like expectation, variance, covariance, and also talked about Chebyshev inequality. All right. So some of these random variables are well understood and well used, and some of the probability distributions are well studied and um, well known, and they have a lot of applications. So in this recording, we're going to talk about some of these common probability distribution functions, and we will study them and we'll see some of their applications. So the first one that we will talk about is the Bernoulli distribution. Bernoulli distribution is simply representing a result of an experiment that has a binary outcome, right? The binary outcome means that it's either one or the other. If we represent that by a random variable, then one outcome will be represented by x equals 0, and the other one will be represented by x equal 1, right? So as long as I have an experiment that generates two outcomes, that's a Bernoulli distribution, which means that I can use this concept for a lot of for a lot of things, right? For a lot of applications. Okay, a lot of these distributions have a parameter. In this case, the parameter that we use for Bernoulli distribution is the p, the value of p, which is small p, which is the probability of success. All right. So, in other words, if I have two outcomes, x equal 1 and x equal 0, the probability of x equal 1 is p, which means that the probability of x equals 0 is 1 minus p, or sometimes I refer to it as q, right? So this will be, p will be the parameter for this distribution. Okay, so the distribution function can simply be represented as this formula, which is p of x equal p of x equal 1, or q if x equals 0, right? And I can write it, well, if you want a 0 and 1, then this means that it's q and p for x equals 0, and this one for x equal 1. I can write it also as 1 minus p. Okay, so what if the outcome of an experiment is not binary, is not 2? Maybe there are more, right? So can I still use the Bernoulli distribution? Yes. You can practically change any set of outcomes into binary outcomes by looking at, you know, the favorite outcome, which we will call it a success in this case, and the others, which we will call it a failure, right? So the success and failure is just whatever you're looking for. It doesn't mean success in the regular sense, but anything that you are looking for. So let's take two examples. Let's take the example of a game, the soccer game, right, that we talked about. And the outcome can be red wins, blue wins, or a tie, right? And this is the set of all outcomes. So I could say I'm looking for the probability of red wins, right? So for this, this will be our x equal 1. The rest will be x equal 0. So in the previous recording, and I assigned 0.7 for red wins, 0.2 for blue wins, and for 0.1 for tie. So in this case, p x equal 1 is 0.7, and the rest for everything else will be obviously 0.3, which is 1 minus 7, right? So I turned the result of the soccer game into a Bernoulli distribution by selecting one outcome, which is the success, what I consider the success. That will be assigned value of, if when considering random variables, the red wins is assigned value of 1, and everything else is assigned value of 0, and probability of x equal 1 will be 0.7. All right, another example, let's say die toss. Here I can say, well, I have the outcomes are 1, 2, 3, 4, 5, 6, right? Let's say I am playing a game and the probability of success for me is getting a number 6, right? So in that case, this will be, all of these will be assigned random variable with a value of 0, and the rest, or x, will be 1. So now the probability of success in this case is px equal 1, and probability of getting 6 is 1 over 6, and the probability of failure is 5 over 6. Head and tail toss or coin toss is naturally binary outcome, and I can assign, if I'm looking for a head, right, I can assign the success as head. If I'm looking for tail, then the success for me will be getting a tail, right? So here, just focus on success means the thing that I'm looking for, the thing that I want, right? Failure is everything else, right? And you can see from the notes that we have already studied this distribution, and we found that the expectation is P and the variance is PQ. So the expectation for us for the soccer game, EX, will be P, or in this case 0.7. For this case, the expectation will be 1 over 6. The variance is PQ, 0.7 multiplied by 3 is 0.21, and the variance here is 1 over 6 multiplied by 5 over 6 gives us 5 over 36. All right. So these are well-known properties of the Bernoulli distribution. You can apply it to any uh, any experiment, but we will see that actually a lot of the uh, remaining distributions are based on Bernoulli. Right? So let's go and talk about binomial distribution. So Bernoulli describes an experiment, one experiment, and the result will be either a success or a failure. Right? If we are talking about multiple experiments, consecutive experiments, like what we did last time when we talked about tossing a coin 3 times, and we wanted to find what is the probability of having 3 heads in a row, right? So that's what we will use binomial distribution for. So it describes the what we call uh, X successes and N trials. Right. So let's take a simple example and go back to the function or the definition in the notes. So let's talk again about heads and tails. So p equal for p of x equal 1, we'll just assign it 0.5 because it's heads, and for tail is also 0.5. It's 50-50. And this will be p, right? The small p for Bernoulli distribution. Okay, so if I am looking for the probability of head, then another head, then another head, then I can say that I have 3 successes in a row. So the probability of getting ahead first time is p. Then getting ahead a second time, probability is p. And getting ahead third time, probability is p as well. So I end up with p to the power 3. How about the probability of having uh, 2 heads and 1 tail? So in that case, let's I don't want to use the wrong notation here, so let's ignore the left side for a second. 2 heads and 1 tail could be a result of head first, head second, and then tail third, or tail, then head, or head, then tail, then a head again. So all of these will result in having 2 heads, right? Probability of 2 heads plus 1 tail. And as we saw in the previous recording, we will get the probability will be 3 out of 8. And this, if you look at all of these, you'll see that I had, if we consider a head as a success and the tail as a failure, we had 2 successes and 1 failure. But that failure could happen at the end, could happen in the beginning or in the middle. Right? For that, it's similar to, so we'll use the notation that we discussed before, which is combinations. So we have the number of trials is n, and then we have the number of successes that we want. So let's call that S. How many failures we had? We had 1. And how many successes? We had 2. So P2 probably I shouldn't write it this way, but anyway. So I wrote it as n choose s, p the power of s, and 1 minus p to the power of n minus s, right? And s represents the number of successes. We can also represent x, use x as the number of successes. So the general formula for this is this one here, where we have n is the number of trials, x is the number of successes that we're looking for, and then how many times we see the success. So that's x, right? So then you imagine that we have a multiple successes, so that will be equivalent to p to the power x. This term here is to give us these multiple combinations. This one will give us the probability of one case. So one case, two successes and one failure. But we have actually three different ways to get the two successes and one failure. So that's why we'll use the n choose x here. All right, so this is our general formula. And again, for this distribution, the expectation is NP and the variance is NPQ. Okay, so this type of distribution has a lot of applications. Imagine we are considering the number of successfully received packets at the receiver. So we say, well, if we send 20 packets, what is the probability that 19 of them arrive correctly? Or what is the probability of 3 of them fail and they're not received correctly, right? So we can use that in many applications. So if we take some of these examples here and see how we use the probability distribution. So here we have a company that's offering promotions, and they are selecting 20% of any new subscribers to receive a discount. All right, so 20 out of any new subscribers, 20%. So this means that the selection or being selected for promotion has a probability of 0.2, right? In P, in this case, small p is 0.2. The question is, if we have a group of 10 neighbors signing for the service, right? What is the probability that at least 4 of them get a special promotion? So when you look at these examples, and some students find the interpretation sometimes hard, you just look for the parameters. So we are looking for P is greater than, so the probability is here we are looking for what is the probability that at least 4 of them get a special promotion. So at least means greater than or equal 4. So we are looking for the probability of x greater than or equal 4. Okay, so that's what we are looking for. That's what you write. First thing you see this, you write, I am looking for this probability. Now I have to figure out, okay, so what is the distribution that I'm going to use? Since this is the probability of somebody getting a promotion or not is like tossing a coin with a probability of success of 0.2, right? We said that 20% will get a promotion. This means that the probability of getting a promotion is 0.2. All right, so that's another thing that we put aside. What is the distribution itself? The distribution, in this case, I have 10 people, and I'm looking for the probability of 4 successes in 10 people, or more, 4 or more successes. All right, so this looks like a binomial distribution, because now I have to look at one person at a time of those 10 people and say, what is the probability of this person getting a success, getting a promotion, right? And then look at the other person, and then the other person, and then the other person. So every person represents a trial, and the success of a trial has a probability of 0.2. The failure is 0.8, 1 minus 0.2. So that's a binomial. Once I figure out that I am looking for binomial, now binomial needs two things, needs n and needs p, and we already figured out x, right? So if you look at the formula, to solve the binomial distribution, I need these numbers. I need n, I need p, I need x. So I got x, that's the 4. N is the 10 neighbors, and p is the 0.2. Right. So now I can solve the problem. So p x greater than or equal 4 is p4 plus p5 plus p6. So the probability of having 4 people success, probability of having 5, 6, 7, 8, 9, or 10. That's the probability of, so we have 10 possible, it's either, or actually 11, either nobody gets a promotion, 1 gets a promotion, 2 gets a promotion, or all of them, right? So now calculating this using the formula that I just mentioned at the top, let me write it down from memory, which is p x equal x, small x here is n choose x, px 1 minus p n minus x, or you can write it as q instead of 1 minus p. So I have to repeat this formula for 4, 5, 6, 7. Now that's a little bit lengthy, right? But I can also represent it as 1 minus p0 plus p1 plus p2 plus p3. That's easier. I'll calculate it only 4 times. So I need 4 or more, so I subtract the probability of having 0, 1, 2, or 3. That's easier because I will calculate the function 4 times instead of 7 times. But remember, last time we talked about cumulative distribution function, and we said that f of x represent probability of x less than or equal x. So if I want to find the probability of x greater than or equal 4, it's maybe easier just to look for or use the CDF. Okay, so now you be careful. We have numbers, the number of x's that, or number of successes can be 0, 1, 2, 3, 4, 5, up to 10. I am looking for anything greater than 4. So probability of x greater than or equal 4 equal 1 minus probability or fx. So should I write 3? Yes, because now I want to subtract all of this. 3 and less, right? Probability of 3 or less, which is x less than or equal 3. So that will be my CDF. Okay, where is the CDF? I have this formula here. Where is the CDF? Well, sometimes the CDF can be given as a function as well, right? And I can calculate it directly. Sometimes it's given as a table. So, and that brings us to the topic of using probability tables. So a lot of these functions are very hard to calculate manually, so we'll resort to using tables to solve the problem. For tables, I'm gonna go and look at one of them right now. So first of all, to use the tables, we need to find the appropriate table for the distribution. In this case, this is the cumulative binomial probabilities, which what we're looking for, right? And you will see here there are multiple tables for different n's. There aren't tables for every possible numbers out there, right? So we'll find tables. So for example, we don't have a table for n equal 5. For n equal 6, we have a table for n equal 5 and n equal 10 and n equal 15. We don't have a table for n equal 12. So that's why you'll see that most of our examples, assignments, quizzes will be limited to these numbers, right? And this should give you a hint. If you see something like n equal 12 and you don't find the table, you don't think, oh, he must have made a mistake. Think, probably I'm looking for the wrong table here, or he's asking me to use a different distribution function. So this should give you a hint. So anyway, we'll practice this multiple times, but let's go back to our function. So we're looking for this number here, the f of 3, or probability of x less than or equal 3. All right, and remember our n is 10 and our p is 0.2, right? So these three numbers I'm looking for. Let's go back to the table. All right, so first, well, I'll use this table because it's n equal 10, and you'll see the columns here. This is for probability 0.01, probability 0.5, probability 0.1, and this is 0.2. So I narrowed my search now to this table with this column, and we're looking for x3, right? So here, if you look at the intersection between the 0.2 at the top, and I'm just going to highlight it for you if I can. Highlight text. Okay, so it's the intersection, or the number that I'm looking for is the intersection of the probability p, which is 0.2, and x, which is 3. So the result is 0.879. So I'll plug 0.879 here, 1 minus, so I'll get the result, which is in your notes as 0.121. Okay, so we saw now that we can use the tables to simplify the problems. If you find yourself doing a lot of calculations like this, means that, okay, maybe I'm doing something wrong. I have to consult the tables. And for many assignments and many quiz questions, the focus will be a lot on using the tables. Okay. This is just a repeat of the last lecture, but if I'm looking for the probability of p x equal 2, right? This should be simple enough to calculate using the formula here, right? So I can put 10, choose 2, p to the power 2, q to the power 8, which is 10 minus 2, right? And I can calculate this numerically. So I can find out the result numerically. But I can also use the tables to, maybe I don't have a calculator, or if I got practice enough, I could do everything using the CDF. So I'm looking for the probability of x equal 2, which is this probability. The CDF always gives me something less than, right? It doesn't give me an actual or one number. It gives me a range. So if I look at the CDF of fx here, minus f of x minus 1, it gives me the probability of x. So if I'm looking for number 2, I can subtract the probability, this one, from this one, so I get only 2. In other words, I can say the probability of x equal 2 is f of 2 minus f of 1, and it will give me the same result. So keep that in mind, that you can use the cumulative distribution function to find the exact probability for a specific random variable. Okay. This is another example here where it's a little bit more, it has an extra step. So an existing computer game is released. 60% of players complete all levels. 30% of them will then buy an advanced version of the game. Among 15 users, what is the expected number of people who will buy the advanced version? What is the probability that at least 2 people will buy it? So here we have 15 users, 60% of them, so not all of them, 60% will go and complete all the levels, and 30% of those will buy the advanced version. So what's the probability of at least 2 people will buy it? So the trick or the difficulty in this question is to find P, right? So now P, first the person has to finish all levels, and then among those who finish all levels will buy the game. So we have, um, imagine we can represent it by, say, this is the people. 65% of them will complete all levels. The others, 0.35, will not complete all the levels. And then among the 65, did they say 30% will buy? 30% will buy, yeah, so 30% will buy, and the remaining 0.7 are not going to buy. Right? So among 15, what is the percentage of people who will buy it? So if you multiply these two numbers, you will get the percentage of people. 15, 65 will finish, and then 30% of those 65 will buy. So the probability, small p, is 0.65 multiplied by 0.3, and we'll get our number here. The rest will be straightforward. So we'll get 0.8 here. Actually, sorry, I think I said 65. It's actually just 60. Right. Yeah, 60%, so not 65. So anyways, you get the result 0.3 multiplied by 0.6, you'll get 0.18. Right? So that's your P. Right? The rest will be just simply apply the formula or use the number, use the tables. So here we are looking for the probability of at least two people will buy it. So again, we're looking for px greater than or equal to, excuse me, and so now we figured p, we figured x, we are looking for n. N is the number of people total, which is 15. All right, so we can say that the probability of x greater than or equal to is the same as 1 minus f, and now we're looking for the number 1, right? So again, 0, 1, 2, 3, all these possible up to 15. We're looking for the probability of 2 or above, so we can subtract 1 and less, right? Which is f of 1. Okay, so if we go back to the tables again, remember we have n15 this time, probability is 0.18. Can we find it? Probability n15, probability 0.18. We don't find it in this particular table, right? So for this table, we actually, this must be, in this case, we don't have the 0.18. So probably we either use a different table or just do it manually. So the number will be close to here, 0.167, right? It will be somewhere less. It will be, if you compare these two, right? So it will be more than 0.67, the result. If we apply the exact formula here, what we need to do is 1 minus P0 plus P1. So the result will be 0.7813. And what I did here in the notes is actually apply the formulas. I didn't go for a table because the tables do not show 0.18. So we had to do it using the original formula here. So you have to keep an eye on these things. One of the things that we can find right away is the average number of people who will buy it. So in that case, it will be easy, which is the expectation, which is NP. So N15, P is 0.18, so we get 2.7. So among 15 users, on average, about 2.7 of them will buy the game. There's a lot of applications for the binomial, so many of them. So you will encounter it a lot. Our next distribution is geometric. The geometric distribution gives us not the number of successes in n trials, but how many trials we need to get the first success. So let's say you are trying to send a packet and the channel, excuse me, the channel has a lot of errors. So you will send the first packet, it fails. You send the second packet, it fails. Third packet, it fails. So you need to find out, given the probability of success and failure, how many attempts you're going to make on what is the probability of making X attempts to get the first success. So actually that makes it easy to find the formula for this. So if I'm making a success, then a success. If I'm making a trial, not a success. If I'm making a trial, and the trial fails, then fails, then fails, and then finally we get a success at the end. This means that I have, for the success, the probability is P. For the failure, the probability 1 minus P. So I need to consider or to find the probability of having 1 minus P to the power X and then P after that. So the number of trials that I need to make is a random number. I don't know how many trials. So I'm just looking for what the probability of that. So the probability of having X equal X is 1 minus P to the power X multiplied by P. So X amount of failures and then followed by a success. And that's what we will call the geometric distribution. The geometric distribution has an expectation of 1 over P and the variance 1 minus P over P squared. Right? Notice that X cannot be 0. Right? So you have to have at least one trial. Right? You cannot, so there's no 0. You cannot apply, or you cannot find the probability of no trials here. So it has to be, the trials has to be one or more. So you have to try. You may get a success for the first time. Right? But since you're looking for the number of attempts before the first success, then you could say the X has to be 1, 2, 3, and 4 and above. Actually, and in my formula, I didn't account for X minus, so I should put X minus 1 here. So in that case, how many trials? Well, the trials include S as well, so you have this will be x minus 1 trials, and then the last one will be a success. So the example that is shown here is a hiring manager interviews candidates one by one, and then, well, the manager apparently decided that the first person that I like, I'm gonna hire, and I stop interviewing. That doesn't happen in reality, but let's assume that's true. So the manager will need to find out what is the probability that I will, um, what is it here? Random variable. Yeah, it looks for a probability of certain number of interviews before you get the good candidate that you want, right? So x can go from 1 to infinity in this case, right? Because we don't know. He may try 100 people and still doesn't like anybody. And he may get lucky and get successful from the first trial, right? So there is no failures. So there is one trial, one success. This is actually not a real example because we weren't given specific numbers, but let's assume that we have, let's turn this example into a specific example, right, with some numbers. So let's assume that in a market with good candidates are hard to get by and probability of succeeding is 0.1. Probability of finding a good candidate is 0.1. So what is the probability that the manager will need more than 10 trials to find the right candidate? So I'm looking for this number. All right, to get to this, I have to find the probability of 10, or actually probability 11 plus 12 plus 13. The x here is the number of trials, right? So I need to find all of these. And it can go to infinity, so that's not practical. I'm not going to count this. So okay, so the opposite, what I can do is find the probability of x of 10 or equal, less than 10 or equal. That's more reasonable. So I can find the probability of P0, P1, P2, and so on, up to P10. Somebody probably by now saying, okay, so why don't you do this? Okay, and which is what we should do. We could go to the tables and find the probability of 10 to find out what is the probability of the manager needs to interview more than 10 people to find the right candidate. If you notice, you will go back to the tables, and do we have a geometric distribution here? We don't actually have a geometric distribution table for this one. So And that's why probably the notes doesn't give us a specific question. Uh, does that mean we cannot solve this problem? No, we can. We can using two cases. The first one is by going through this formula manually and solving for every x from 0 or from 1. Oh, I made a mistake again, didn't I? Right? Yeah. So there is no 0 here. Right. So you would have figured it out by looking at the formula, right? So let me go back. And so you can solve it by looking for x equal 1, x equal 2, up to 10. Or, as we will see later, we will have a different way to solve this. So we will solve it, but in a different way, right? Without tables and without doing actually the calculations for every x from 1 to 10. All right, so we'll keep that for now and revisit later. But before we leave, we can actually find the average. So if the hiring manager is looking just for what is the average? What is the average of how many interviews I'm going to make on average to get the right person? So in this case, it's 1 over P. And 1 over P, I assume that P is 0.1, so 1 over P is 1 is 10, right? So the expectation here, which is 10. So on average, the hiring manager will interview about 10 people to get the candidate. The next distribution is called negative binomial distribution. And this should give you a kind of a hint on the nature of this distribution. So we looked at the binomial distribution, which looks for or represents the number of successes in n trials, right? So we'll say, okay, how many successes we need, how many trials we need to get n successes. This one is looking in the problem, or looking at the problem from a different perspective. Here, I'm looking for the number of trials to get X number of trials to get fixed number of successes. So the X here is the unknown, which is the number of trials. So let me repeat that again. So in the binomial, I have fixed number of trials, n trials. That's fixed. And X, which is the number of successes, is unknown. So that's the binomial. The negative binomial, the number of successes is fixed. But the number of trials, or so in this case, because it's a random variable, the X will represent the number of trials, and it is unknown. N here represents the number of successes, right? So N and X switch positions. For the binomial, the X is the number of successes, which is the unknown, and the N is fixed, which is the number of trials. And the negative binomial, the successes are the ones that are known, and they are N, and the trials that the ones that are unknown or random, and they're given X. All right. Okay, so in that case, the formula is this one: x minus 1 choose k minus 1, with k is the number of successes here. Okay, so and we have the expectations, which is k over p, and the variance, which is k1 minus p over p squared. Now, again, if I go back to the tables, I won't find a table for the negative binomial. So that's two tables that we cannot find in these set of tables. Think, okay, so how useful are these tables? uh, the reason is actually because we can find the results for the negative binomial by looking up the binomial tables. So we don't need a special table for them. But you need to do a little bit of a modification, given the fact that negative binomial is the, uh, the opposite side of binomial. So in this example, uh, we have in recent production 5% of certain electronic components are defective. We need to find 12 non-defective components for our 12 new computers. Components are tested until 12 non-defective ones are found. What is the probability that more than 15 components will have to be tested? Right? So here, if we dissect this step by step, let's start from the last sentence. What is the probability that more than 15 components will have to be tested? So this should, if I were a student, and even now when I'm teaching this, the first thing I do, and you probably noticed by now, that I don't memorize a lot of things. So I don't memorize answers. You'll see sometimes I make mistakes while I'm explaining because I don't memorize things, but I look at the problem fresh every time. So what is the probability that more than 15 components will have to be tested? So let's put that down in writing. The probability of more than 15 components to be tested. So that's x greater than 15. That's the probability that I'm looking for. All right. Let's go back and read the same question again. 15% of certain electronic components are defective. Okay, so that's our P. The probability here is 0.5, so or it says 0.5%, which is 0.5, yeah, 5%, 0.05. So that's the small p. And then if you read further, we need to find 12 non-defective components. So what we're looking for is how many components we need to test. So we need to find 12 successes. The successes are given to us. That's 12. But the unknown or the random number is the trials. All right, so that should direct my attention immediately to the negative binomial distribution. I need to find 12 components. So how many tests I need to get them? Now, geometric will be one success, right? For geometric, it's like one success. How many trials we need to get one success, to get the first success? Here, we have more than one success. We have number of successes. We have 12 of them. How many trials we need to get the 12? So that should give you distinction between the geometric and the negative binomial. They look similar, right? but the geometric looks for always one success, but the trials are unknown. How many trials? For the negative binomial, we have more than one success, and we know we need to find how many trials. Okay, so we figured that we need to use a negative binomial, and our successes k is 12, which is this is k, or k minus 1 is the number of successes. So I have, but I'm not gonna use the formula. K is the number of successes, X is the number of trials, and all of that. So if I want to do that, and remember here, or see here, that X has to be K or more. Why? Well, I cannot have 12 successes in one trial. I cannot have 12 successes in two trials. So the trials have to be at least 12 and then up, right? So I could be lucky and test 12 components and find 12 components in 12 trials. So that will be luck, right? Good luck. But so X starts from K and above. Same thing with the geometric. X has to start from 1 and above. I cannot have a success from no trials, from 0 trials. Okay, so these are the things that you need to keep an eye on, but implementing the P of X here, or solving the P of X for all the values, were going to be difficult. One difficulty is going to go, it may go to infinity, right? So there is no upper limit for this. So if I want to calculate Px greater than 15, I have to calculate x equals 16 and so on. Even if I do 1 minus, that will be also a long way to go. And I told you already that we don't have tables for negative binomials. So what should we do here? Well, if you look at it from a different perspective, you can turn it into a binomial distribution instead of negative binomial. So we know that the question is, what is the probability of having more than 15 trials to get 12 successes? Right? This is similar to saying, what is the probability of having less than 12 successes in 15 trials? All right. So I did 15 trials and I didn't get 12. So I need more than 15 to get the 12. So I can turn this into the equivalent of, I can say, this is equivalent to saying give me what is the probability of having less than 12 successes in n trials, n 15. Why did I use y instead of x? Because now this is a different distribution with a different random variable. So I turned it from a negative binomial to a binomial distribution. And since I have tables for the binomial, I can look up the tables. So the table here, n is 15, right? 15 trials. So I can go to the table that says 15, and our probability is 0.05, and we're looking for 12 or less than 12. Less than 12, which means 11. And I may have chosen the wrong table here. Let me see. Oh, what I missed is now we flipped also the probabilities. Instead of having p as zero point 0 or a zero point 0.5, we're looking for the opposite. So now our success is considered the failure in the previous. So, or the failure in the negative binomial will be the success in the binomial. So p is fixed or is changed into 1 minus p. Here in the negative binomial, the probability of having a defective components is um, 0.05, right? And we're looking for how many trials before we get the 12. If we flip it, so our probability of success will be 1 minus the original p, right? Okay, so now I have to go to the tables, and instead of looking at this one, I'm looking for this one here. And again, go to the 11, intersect. So I'll get this number here. So this is the intersection of 11 because we're looking for F11 and the probability 0.95. So we will get this. I must have used a different table because now the answer is 0.0055 while our table shows 0.005. So the answer, so um, different tables give different precision. Some of them they have 4-digit precision or 4 decimal point precision. Some of them have only 3. So this table has only 3 positions, but the result is, you can see it's the same. Okay, so we'll move on to the next one, different distribution, which is Poisson. Poisson also one of those very common distributions that has a lot of applications in communication. And one example, for instance, one example is it can represent the number of packets received by a router in a specific time, right? So I can say, what is the probability of having 5 packets received in 2 minutes, right? Or uh, how many phone calls the operator can receive in an hour. What is the probability of having 5 calls in an hour? So these events, the packets or the phone calls, we call them rare events. Why we call them rare events? Because the assumption for the Poisson distribution is that they cannot happen simultaneously. When you receive packets, you're not going to receive packets at the same time, not in the same interface anyways. If we assume that the events will be spread apart enough that they don't happen at the same time. If you have a case where things can happen at the same time, then you cannot use Poisson distribution, right? So if you have a scenario where you're looking for parallel processing or things that can happen at the same time, events can happen at the same time, you cannot use Poisson distribution. So we're looking for things that do not happen simultaneously. And that's why we call this rare events. One thing interesting about this Poisson distribution is that it's the first distribution so far that doesn't have P as a parameter. We're not looking for a probability here. Instead, we're looking for average number of events. So the parameter that we use is mu. It's not P. The X is still X, so the number of events is still random. But instead of looking for the probability of event happening, we're looking for the average number of events per unit per time. And that makes also the expectation is the same as mu and the variance is the same as mu. So that's easy to remember, right? And also this, anyways, we'll see what else is special about this Poisson distribution. So think of it as if I have a period of time here, let's make it a little bit more horizontal. So if I have a period of time and there is the events happening, if I know what the average is, then I can calculate the probability of certain events. And sometimes when I ask a question, you should think about it, or you should apply some intuition, right? So if I say the average for events is 5, for the average of having certain packets arrive to a router in 1 second is 5, right? What's the probability that we'll have 10 or more than 10, right? So if the average is 5, having more than 10 arriving, the probability should be small, right? Because the average is 10. Probability of having 0 arriving should also be small. Probability of having 4 arriving should be big because it's close to the average. So you should think of it this way. But anyways, we'll get to that point later. About thinking about the result before even you get the result, because sometimes if you just apply numbers without thinking about them, it's very likely that you're going to get or you're going to make a mistake. And there are a lot of things that I do here, and I realize that I make a mistake by looking at the number at the end and say, well, that doesn't make sense, right? So maybe I made a mistake, so let me look back and see what I did wrong, right? So you use intuition sometimes uh, to verify yourself, to verify the answers, rather than just put numbers and type or push the calculator button and get the answers. Okay, so and that comes with practice as well. So let's see. There is an example here that says customers of an internet service provider initiate new accounts at an average rate of 10 accounts per day. What is the probability that more than 8 new accounts will be initiated today? Okay, so here the average mu is 10, and we're looking for the probability of having more than 8. As I said before, let's take it step by step. So we're looking for a probability of x greater than 8. And we were given average of 10. And if you look at the example, you will see that internet service provider initiate new accounts at an average of 10 accounts per day, right? So that's an interval. Day is interval. So when I look at, I was given average, and the interval is day, and then I'm asked to what is the probability of having certain events happening. So that's Poisson distribution, right? Some people will mistake it with binomial, right? You will probably think, oh, binomial. But wait a minute, binomial has trials. It's not interval. Here we have interval, we have a day. Binomial gives us P. The parameter is P, gives us the probability of success. Here we have an average, right? So you have to differentiate between the two immediately. So the probability of having more than 8 new accounts, so that's P of x greater than 8. Again, if I want to apply this formula, this means that I have to apply the formula multiple times, which is not practical. But I can go to the tables. I can go to the tables by looking for the probability of x greater than or equal 8 is 1 minus probability of x less than or equal 7. Less than or equal 8. Why? Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 events. I'm looking for the probability of this, right? Greater than, I made a mistake again, but drawings is always good. So I'm looking for greater than 8. So what I need to calculate is 8 or less. See, writing all of these numbers always help me. So I hope you follow the same lead and try to put on your worksheet, put on the side these numbers and have the ranges so you don't get mixed with the greater than or equal than or all of these. Sometimes, and especially when you are in a hurry, you will get things confused. So I'm looking for this, which is f of 8, right? So let's go to the binomial table and see what we can find. So the binomial, here is binomial. Sorry, not binomial, Poisson, sorry, Poisson. Poisson, the average is, in our case, is 10, so this doesn't work because the tables here show 0.1, 0.2, so that doesn't work. Here we have an average of 10, so that's good. And we're looking for the probability of 8 here. So that's 0.33. Trying to highlight it again. So here. So that's 0.33. So if I plug this number here, I get 0.667. And that's my answer. Okay, so the next one here is what is the probability that there are more than 16 accounts will be initiated within 2 days? Okay, 16 accounts initiated in 2 days. So if I do px greater than 16, right? Here you have to be careful. Look at the interval. You cannot use the same mu again. Why? Because this mu was for 1 day interval, for 1 day. The average for 1 day is 10. But if I'm looking for 16 in 2 days, then I have to find what is the average numbers in 2 days. So in this case, let's say mu bar is 2 multiplied by 10, mu prime here. So the average I have to increase the average, multiply it by two days. If somebody asks you for a week, then you have to multiply it by 7, right? So now I can repeat the same thing, but with a mu of 20 instead of mu of 10. So as I did before, I will use table with a mu of 20, and I'll look for the x equals 16. So let's go back to the tables. 20 is here, 16 is here. So if I do the intersection, I'll get this number. It's 0.221. Which gives me 977, I think. Yeah. Okay. So that actually finishes all the distributions that we are going to talk about in this lecture, in this recording. But we'll see here that we have something, and this is a hint of other things that we will talk about in the next recordings, is sometimes we can approximate the one distribution with another. So Poisson and binomial have certain things in common. Poisson gives us the number of events in a period of time. Binomial gives us the number of successes in n trials, right? Imagine if the interval in Poisson is divided into very, very, very small pieces, like the 1 day is divided into minutes. And if I ask, okay, how many events happen, or how many, I can make it look like a binomial, right? I can say, well, 16 successes in n minutes, right? Or 8 successes in n minutes instead of n successes in 1 day, right? That helps us actually approximate the binomial with Poisson. Binomial, if you go back to the formula, has the factorial in it. So this factorial element, n choose x, and then n here as the exponent, makes the numbers here very large. So if n is, let's say, 100, and I want to find the probability of x equal 5, then this will be 100 choose 5, which is going to be a large number. This is n factorial divided by n minus x factorial divided by x factorial. So a huge number. And q to the power of 100 minus 5, that's q to the power 95, also a huge number, right? So at some point, calculating this becomes a challenge. But because Poisson can be made to approximate binomial, I can actually use Poisson instead, but with some modifications. So first of all, I have to make sure that n is greater than 30. So the number of trials in the binomial is greater than or equal 30. and P should be small, should be less than 0.05. If I have these two conditions, then I can approximate binomial with Poisson, which means that I can use binomial to calculate the Poisson, I can use Poisson to calculate the binomial distribution. All right, so how can I do that? Well, first of all, remember mu here. Where do I get mu? Poisson needs mu. Well, I can get mu by n multiplied by p, which is here. That's my mu, right? Okay, so in any problem that requires, if I have a problem that requires solving using binomial with n and p, I can approximate it by using Poisson. I hope I didn't spell it wrong. With mu. I think I spelled it wrong, but anyway, mu equal np. All right, n has to be greater than 30, and p has to be 0.05. If this is the case, then I can simply plug, instead of having x found by binomial, I can have it by Poisson instead. All right, so what happens if n or p is actually very large, not very small? So for if p is actually very large, closer to or greater than or equal 0.95, I can still use by Poisson, but I have to flip my success. So let's say if I'm looking for what is the probability of having x greater than or equal 3 using binomial, so that will be the p here will be the number of successes, or related to the probability of success, not the number of successes, but the probability refers to the probability of success, right? So what is the probability of having more than 3 packets arriving in 1 minute with a probability of success is 0.95? So I can convert it by saying, what is the probability of having less than 3 failures, all right, with p is now the probability of failure is 0.05. So what is the probability of having less than 3 failures? And then I can use Poisson for the approximation. So this is what the table here, or this is what the example here is saying. So if I go down to the 97% of electronic messages are transmitted with no errors. What is the probability that out of 200 messages, at least 195 will be transmitted correctly? So you can see here that I have large numbers here. If I want to use binomial, I'll be having a hard time. Immediately I can say that P is 0.97, N is 200, X is at least 195. So it's binomial distribution, right? But the N is very large. So if I want to apply the formula, first of all, I won't find the tables for 200. And second, if I want to apply the formula, the numbers will be astronomical. I cannot calculate it. So that immediately should give me a hint that I need to use Poisson distribution. But the challenge here is Poisson distribution works only if P is small, and P here is not small, it's 97%. So P is 0.97. So what should I do? Okay, so instead of having, and I'm looking for Px greater than 195, Px greater than or equal, at least, so so it's greater than or equal. And n is 200. So I cannot use Poisson directly because P is large. So what if I look for failures instead? So out of 200 messages, maybe I should look for the probability of less than 5 messages fail. The probability of failure here is 0.03, right? N is 200. So if calculating mu 0.03 multiplied by 200, I get this number here. So instead of recalculating everything, it's 6. Right. So here the table uses Q is actually, this is just to tell you that I calculated 1 minus P, right? So the P that I'm using for the approximation is 1 minus original P, right? So 0.03 multiplied by N gives us 6 here. So I'm going to calculate this with the tables. So the tables, mu is 6, and I'm looking for less than 5, which is this number here. And that is the result. And this is how you apply the approximations. And that concludes the chapter chapter 2 that talks about the distributions, discrete distributions. So next will be the continuous distributions, right? So thank you for paying attention, and I will see you in the next recording.